All right, finally. Hi, Zoe. Good afternoon. First of all, I apologize. Monday, I sick a little bit, and my message was really late. I heard that some of you actually show up here without knowing that the class was canceled. I'm not sure if you could get instantaneous SMS messaging or email directly from the. If you, I think there's a function that you can actually subscribe to the announcement. They can actually send you your SMS. That's probably more efficient. But anyway, I apologize. Was just really not feeling well the other day. Still not 100% yet, but good enough. So just check with the online side. Hey, Andrew or Jerry, can you guys hear me well?
Yes, sir. Can you hear me?
Hello? Hello, hello?
Oh, it's audible, Professor. We can hear
Can you
you.
hear me?
Yeah.
Okay, great. Thank you. Okay. So on Monday, I uploaded a recording. I'm not sure if you actually review it, but I think there are some points I want to review anyway with you because those are some of the key concepts that will carry over to today's main topic, which is introduction to neural network. So just want to spend about 10 minutes, 15 minutes to go through module one. That we will be using quite a bit moving forward. Just basic concepts. Okay, so just bear with me. The idea of different learning type, so if you review the recording, so what's supervised learning? What is supervised learning? Go ahead. Data are labeled, meaning no fact. Unsupervised, on the other hand, not labeled. Okay. The output is input, obviously, is the given, right? How many of you actually know reinforcement? In a nutshell, that's what it is. But anyway, I will still, spend a minute on that. This is the main page I want to establish a concept. Okay, so I want to formalize the meaning of learning in semi-mathematical fashion, not a rigorous. It's not a rigorous theory or mathematical equation, but I just want to kind of give it a formulation. So essentially, we are equipped with data. The data, a lot of them are inputs, some of them are outputs. Whether you label the output or not, determine whether this is supervised or unsupervised. Right? We'll give examples about those two a little bit later. And what machine learning try to do is to find out the relationship between the input and output, right? Either find the underlying pattern or identify some process, right? So you can assume there's a function that we don't know exactly what it is. Okay? You can think about it as a function that you know is like a linear, maybe a multi-degree polynomial. It's something that is very structured. But usually it's not. It's not something that we can easily describe. Right? That's the reason we want to use machine learning. But there is a function that we want to find out. So mathematically, you represent your training data as a pair of input and output, right? And you try to find some hypothesis, multiple hypotheses, actually, that can approximate to this target function. So that's kind of the mathematical formulation of learning. And learning really comes from changing the hypothesis iteratively until you find, quote unquote, optimal solution that closely approximate test the target function. So let me give you a supervised learning example. Very popular application, credit card approval. Your bank will receive credit card applications based on your salary, credit score, your debt situation, right? A lot of data. And so that's X, right? Your X are your credit history, your salary, your debt level, your asset, for example. And the outcome is pretty simple. It's either approve or reject. Let's just make it simple. Sometimes they approve with different level of spending, give you $10,000 credit. Sometimes they give you more, but that's not the point. The point is output is either I approve it or I reject it. So that's the output. So exactly what is that credit approval model? We don't know. We'll figure it out. So the training data in this situation is a whole bunch of historical data based on previous applicants. You have millions of applicants. You have millions of sets of data. There are results. There are applicants' profile, right? So that's your training data. And finally, you want to come up with a set of hypotheses that approximate this video approval modeling. So the learning outcome, as I said, is to iterate to etch the hypotheses to eventually get an F. So keep this in mind. We'll come back to visit this definition a little bit later. Okay, supervised learning. We already know. We are given a pair of known input and output. Okay, so I'm not going to stay here for too long. Typical task classifications. There's so many classification problems, right? Facial recognition based on known faces, known label, because I know that's thing, right? And let's begin. So if I encounter a stranger that's not in the database, then they'll be rejected, or somebody that's already in this class has the photo being recognized. That will pass the facial recognition algorithm. So that's classification. A lot of the problems in the world belong to classification. Regression is another class, very classical, usually deal with real numbers, continuous values, okay, based on the inputs. We use this fancy term for features. I'll explain what feature is, because we are going to encounter this term called features very often. I'll kind of expand on it a little bit later. So the basic task for any regression work is to make a prediction based on the real data, based on past data, come up with a model, and you use that model to make a prediction. Okay, so that's called a regression task. I'll skip those things. So that's the regression, right? You want to predict stock market based on the past history. That's real number because the market information is our real data, right? Our real numbers. Unsupervised learning, your output is not labeled. So basically your algorithm has to figure out exactly how to how to cluster them, for example. Find self-recover those underlying patterns, similarities. A lot of things can happen for unsupervised learning. But it's very important as well. I'm going to give you one example, very typical example of clustering. So, you use customer purchase data or customer credit card application data, right? You have a group of people from different background with different profiles, right? And you want to kind of put them into different categories, right? People like you guys between 20 to 30, young, unmarried, and college degree, right? That's one category. Me, deal with a middle age male with 2 kids, a wife in a house in suburb. This another category. Right? But there is no a set rules to cluster people, frankly speaking. So clustering is a way that consumer service provider keep using to put consumers into different categories, or different clusters. And they can, based on the common characteristics of that cluster, and devise marketing strategy. Right? So that's called clustering. Now, there is no label. There's no labeling when you receive this input data. It's no labeling. It's just raw data of different profiles. So what you want to do is that you use unsupervised learning to come up with a model. You recognize the pattern. You probably just divide them by their education background as well as their income level and their age. That could be one group, right? There are different ways that you can actually cluster people. And that's a very, very typical, popular example of unsupervised learning. So whenever you have new customer data coming in, you know where to put them into different bins, and that will make the customer campaign much easier. Okay, this is another very popular example, right? When you go to Amazon, you purchase a book, you always end up with a lot more recommendations. Right? So why do we have those recommendations? What do you think? Why do we? Of course, Amazon wants to sell you more. That's their motivation. But how do they come up with all those similar products and think that you will like it? I would have history for sure. Yeah, but they also think similarity, right? Because they put you in a certain cluster, and that cluster of customers happen to buy those books, so they think you might like it too. Maybe it works like a charm, right? It's actually worked pretty well. So that's a typical example that's been really popular in using in unsupervised learning. Okay. Quickly go over reinforcement learning. The central idea really is that the decision maker, in this case we use a decision called agent. Probably heard about agent a lot in recent AI development, but agent is simply a decision maker, an entity that take action. Reinforcement learning it is super popular in robotics. Okay. So you can think about this agent as a robot. That you want to teach a robot to move from point A to point B or go through a maze. Usually you just allow the robot to learn by using reinforcement learning, which is pretty straightforward. There is certain thing called policy, means that what should the robot do next? That's called policy. But that policy is updated, constantly updated based on a feedback loop. Meaning the agent take an action. You move the robot move 2 steps forward and realize there is a wall, an obstacle right in front of it. So he actually got a feedback. That's called a feedback. And that feedback is either a reward or a punishment. A reward means that, hey, good job, keep going, you're in the right direction, or you keep the walk. And that's a punishment, as you know, you are now moving forward, you actually be not backward. That feedback is in the form of a reward or a punishment. Okay. And that is also in the form of the state of the environment. So the environment for a robot is this whole room, for example, if this is a maze. Whole room is the environment. They give feedback and give the current state back to the agent, the robot. And the robot started to change the internal policy to internalize it and make that learning, start to learn. And the objective for reinforcement learning is to maximize the overall accumulated reward. Go ahead.
Kind of confused about what part. Is it like pure feedback, or is the reward some sort of numerical value?
It can be a numerical value and in points. For example, you do it correctly, you get 50 points. You do it wrong, you get minus how much? One. Okay. Good question. So then you can accumulate your reward, right? So at the end of the day, you want to accumulate the maximum rewards, and that's the whole reinforcement learning is based on.
The reward depends on the state that the environment
Exactly.
would be in.
Exactly. So actually a funny video. Sure if you guys see this. This is how reinforcement learning works. So if you look at the chicken that's packing the food, did you notice the pattern? The chicken actually recognizes whenever it peck on the purple one, pink one, it gets a reward. You notice that? So after a while, the chicken knows it. So that's a reinforcement because the chicken got a reward by pecking at the right color. Right? So that's a fun way to kind of understand reinforcement learning from a robot standpoint. The robot actually do the same thing. It recognized, oh, if I go this route, I get 100 points. And next time I will continue to go that route, right? I will continue to do that. Now, of course, this is a very simplified scenario because there are only columns for the chicken to pick. But if you have different scenarios, the robot eventually will figure it out, find the best path that give the robot the best reward. So just give you some intuition. Okay, we are not being rigorous here because this is not our main focus. Nevertheless, if you want to learn reinforcement learning, this can be a one semester course. Okay. It's a whole book dedicated to this task. Okay. I do want to kind of just quickly go over linear regression and logistic regression. Just give you some concept because those two are the basis for neural network. Because you are going to see those two are kind of a special case for neural network, but they are classical machine learning algorithm. They are also statistic-based algorithms. Okay. They are pretty important in machine learning. So linear regression really, I'm going to skip those examples because they are not really relevant. Linear regression works the best on tabulated data, meaning structured data. Do you remember what a structured data is? Tabulated. Okay. So this is a typical example of a tabulated data. So you have columns, you have rows. That's a real estate example. We have price as a target because we want to kind of predict the price of a property. And those are the attributes or features of any property. Each row is a problem. Number of bedrooms, number of sizes, the sizes of the bedroom, for example, or the area population. This is a very simplified example of a typical real estate table data. So at the end of the day, you want to use those historical data to come up with a model. So you can predict the price of an unknown or a new property. So that's the whole purpose of regression, linear regression test. Those are the kind of the terminologies to describe the items on this table. So observation means one row of data is one property. Columns means input features. You could have hundreds of features to describe a property. Right? Price is our target because that's what we care about. We want to know the price. So that's our target. That's our Y. And all the others are X. Okay. So what's important is the formulation of how do you formulate the hypothesis for linear regression. So this is the easiest form because the output or the prediction based on a hypothesis on the input data is simply a linear combination of the input features. All the weights, A0, A1 to AN, we call that weights, are the parameters that we want to estimate in order to get that edge. So this is called linear regression. So basically, it's a linear combination of input features, X. So our job, the job of a machine learning algorithm, in this case, is to predict A0, A1, A2, all the way to AN, because those are the weights that determine the model. And in turns, determine the predicted output. Okay? That make sense? Question so far? Make sure you understand this, okay? So the question is, if we are given a data set X, how do we actually compute A? The parameters. But it turned out for linear regression, there's actually closed form. But that's not the key point for this class. I just want to kind of give you an idea that linear regression, being the most fundamental machine learning algorithm, actually has this format that we will see again and again and again. Okay, logistic regression. So logistic regression is different from linear regression. Linear regression deal with real numbers. Your input are real numbers. Your outputs are real numbers. So basically, they are numbers. But logistic regression deal with classifications. The input is real number, but the output is classification. It's the classes. So what do I mean by class? I'll give you a couple examples here. One is, your blood type. Blood type. How many blood types do we have? Let's not go into too much granularity, but basically we have A, B, O, AB. Those are four major types. So those four are called classes. Classes. Class A, class B, class AB, class O. So essentially your output are one of those four. If you are given some of the data and you try to identify what is the data, the blood type, it has to be one of those four. Okay. Same thing with medical diagnosis, right? If you have a tumor, sorry, that's a bad example, but just happened if you do have a tumor, you gotta remove, then you send it to the doctor for diagnosis, right? So either you get a benign output, which is good, or you actually get a cancerous diagnosis. So the output classes are either 0, which means good, benign, or 1, that means actually cancerous. So those are classification problems. We typically deal with finite number of outputs instead of real numbers. It can be anywhere between minus infinity to infinity. Okay? So that's logistic regression. The target is to perform classification. I'm going to skip those, but I just want to give you the kind of map the get a connection between linear regression to logistic regression. Okay, so since the logistic regression is actually let's use binary, right? Your output is either 0 or 1. It's a binary classification problem. Then your output is pretty much only have 2, right? There's nothing in between. So if you take the take it back. So your input is still real numbers, and you make a calculation based on linear regression, right? And you get an output which is a real number. And based on that real number, how do you make a decision? So then you have to have some threshold to make a decision whether this is a 1 or 0. Okay? So one way to do this is to really map that linear regression output into something like this that can give you a decision on either 0 or 1. And there's a threshold pretty much kind of in between, halfway, to tell you if you're above that value, you classify that as 1. If it's below, you classify that as 0. So that's the basic idea of turning a classical linear regression into a logistic regression. And in order to do this kind of operation, we use a function called sigmoid. Sigmoid function allows you to do things like this. That's sigmoid. Very, very simple. Very, very simple. So this sigmoid function will eventually map any real number into a range of 0 and 1. So if we just do a quick exercise, if you have a real large number in Z, what will be the output of GZ?
Very large.
For a very large Z,
Oh, still gets to 0.
very large Z,
Oh, I'm sorry.
because E minus Z will approach 0, right? So this will be 0. So yeah, you're right. This will approach 0, but GZ will approach 1. And vice versa. If Z is really small, minus infinity, then this E minus Z will be so big, I turn GZ to 0. So the good property of sigmoid is that it turns large number into 1, small number into 0. So you limit the output to between 0 and 1, and that is very good for binary classification. And there's also a very good property that the midpoint of Z equal to 0 is exactly half of 5. So that's sigmoid. We'll see sigmoid pretty soon. But I want to give you the basis for logistic regression is to use sigmoid. So that's the relationship between a linear regression to logistic regression, is to turn this linear function into something like the sigmoid curve. That's the whole idea. A linear model to a logistic model. And how do we actually interpret those regression functions? So just remember this, okay? Because this is between 0 and 1. So you can think about those numbers as probability. Okay? So that's what is the statistical meaning of the logistic regression outcome. If you get a number of sigmoid output of 0.7, that means the probability of you getting a 1, which in this case may be a cancer cell, is 0.7, 70%. Then that means you will classify that as a 1. On the other hand, if you get a 0.3, that means it's below 0.5. You can classify that at the end as a 0. Okay. So any of those medical diagnosis is never 100%. It's never 100% or 0%. They're all based on some probability measure. If it's close to 1, they will say, no, yeah, I think you have it. Or they will sometimes say, if there's an 80% that you get cancer cell, right? Or 30% of, 30% chance that you actually are, your tumor is actually benign. People will say something like that. Always quote a probability. And that's the reason, because it is a probability at the end of the day. Okay. So to recap, those two foundational machine learning algorithms, linear regression and logistic regression, serve two purposes. One of them is to serve a prediction of real numbers. The output is real number. The other one is for classification. That's logistic regression. Okay. Do go back to my recording to get more explanation. But I want to kind of set this up for today's lecture because we are going to talk about neural network. Okay. And I want to first give you some motivation. Yeah, why do we actually need neural network? Well, as a matter of fact, neural network happened much earlier than those classical probability statistical based model. Last week in the first class, I mentioned that actually neural network was first studied in the 40s. And in 1957-58, Dr. Rosenblatt in Cornell proposed the first computational neural network model. So it happened really early. But I want to kind of do it in flip it because we introduced the easier one first. I want to tell you, actually, they are not going to be really helpful for complicated or unstructured data. So what is unstructured data? Give me one example. Well, there is actually an easy answer. Anything that is not structured is unstructured. So, but example, what's unstructured data? Image, text, excellent. We deal with it every day.
I'll say something else.
Yeah, thank you very much. Image, text, audio, speech. Right. Go ahead. Yeah.
I was thinking something that wasn't on the slideshow. That's
No, it's okay. It's okay. Structured data is pretty easily handled by linear regression. Okay. Structured data you want to do classification can be handled by logistic regression. There is a host, maybe more than 80% of the world is full of unstructured data. Then those two classical methods kind of fall short. Those are the things that we don't cover, so it may not make a lot of sense to you, but classical statistical-based machine learning require a lot of human interaction, meaning I have to do some quote-unquote feature engineering. I have to add a lot of pre-processing on the features in those columns, okay, to derive more insights to help my machine learning. Okay, so that means a lot more work. And also a lot of the underlying features as we progress through the semester, you will realize neural network is really good for deep learning for a reason, because they are detecting the patterns that we don't see. We don't see at all. It will amaze you. And that's really not something that can be easily achieved by those classical models. The other thing that's pretty much dominating all the data set is the data set itself is nonlinear in general. Nonlinear data set. I want to give you some fun example. So you see blue and orange on this chart. So how do you draw a boundary? How do you classify it? For a circle. A circle is nonlinear, right? Circle is nonlinear. How do you classify the middle one? We have 4 quadrants. Have a cross. Okay. Well, you can call that one linear, but it is not a linear that you actually have a boundary just have a 0 and 1. You do have to do it twice. Okay. How about the third one? Called a spiral.
Some weird trig function.
Right. So, but one thing you can conclude very quickly is that it's not simple, right? It's not simple to actually classify the orange from the blue dots easily. So in general, they are structured data, but they are nonlinear. They need nonlinear operations. Okay. Both logistic regression and linear regression fall into the category of linear classifier. So it's very hard to deal with those. And if you want to use classical methods to deal with those nonlinear data set, you pretty much end up with a large number of features that you need to add in order to perform successful. Okay. Yeah, I love dogs. So if you want to classify a dog, you represent the image by something like 50 by 50 pixels. And each one of them, because it's a color image, so you have R, G, and B. Right? You understand this part? The color has 3 components, right? Red, green, and blue. So to represent an image, you need a lot of pixels. Right? Even if this one is just 50 by 50 means 2,500 pixels per color. You have 3 of this, so that's 7,500 pixels. Okay, that's a lot of data point to represent an unstructured data like that. So, in order to capture the relationship between pixels, which is basically what our classifier wants to do, is to find those relationships between pixels in order to figure out what is that, a dog or a cat or a monkey, right? So you will need a lot of nonlinear terms that can easily add up to millions of features. So this is not going to work. So neural network is probably the strategy that we need to use anyway, because the classical way just simply doesn't work. I'm going to skip those and I'm going to jump right into what I really want to talk about today. This portion will probably require 3 lectures, and that's how we will attack this topic. So I put a roadmap here. Today we are going to cover the first part. I don't think I can finish, but we'll try. Okay. The way I teach neural network is especially the classical neural network architecture, which is our foundation. Okay. So we are covering the foundation in the next 3 lectures. My objective for you is not to introduce to you a lot of theories. I do have some theory, but it's not my main point. I want you to be able to intuitively retell and tell other people, explain to other people why neural network works. What is neural network and why it works? Why it can solve problems, almost any kind of problem. I want you to be able to do that. So, and that's the way I will explain that to you. Now, of course, There are a lot of very complicated algorithms that's really hard to explain. But I want you to have at least the confidence to explain to people at the end of the semester that you know why neural network works. Okay. So this is the foundation. Okay, let's go through it. Let's go back to Dr. Frank Rosenblatt. He's a pioneer, right? 1957, he proposed a paper for the early model of the perceptron. He actually proposed something more sophisticated. He tried to explain how human sensory work with the brain. Okay. Now, I'm not a neuroscience scientist, so I'm just going to capture some of the essence. So essentially, if you think about our sensory units, such as our eye, we have retina, right? Retina capture images. It's basically a sensory device. Doesn't really recognize if that subject is a person or a car or a bike. It just captures. It's a sensory unit. That sensory unit send the image or signals to our brain. And our brain has the ability to associate that image to something that we already know in our memory. Usually stored in our memory cells, right? So there is an associated, I shouldn't say, and a bunch of associated units that pretty much take the sensory unit input. But that's not it. Okay? So our brain, started to figure things out, trying to associate this with past experience. There has to be some action. So the third part of this is a responsive unit, is whether we really make a decision about what that particular subject is. Make a decision, really knowing, recognize. That's the simplified version of Dr. Rosenblatt's original idea. But he took one step further. He said this is a little bit more complicated. Let's simplify it. And that's the famous perceptron. The building block of any neural network is a perceptron. So and we talked about perceptron a week ago. Now let's give it a formal definition. So perceptron is it's basically a processing unit, a neuron that take the inputs, like those sensory inputs, X1 through Xn, that's just a notation. That's different number of inputs. And you weight them and add them together to form a signal. So again, this is something that we just saw, right? Linear regression, the first one, is the linear combinations of the input signals, but we added a weight, right? So that's the first part of the neuron. Over here, that's the neuron, right? That's the first part of the neuron. And the second part is an activation function, but activation function corresponds to the responsive units here. So it's an activation function. In a classical sense, in Rosenblatt's original perceptron definition, the activation function is a simple threshold. It's a simple threshold logic. If the summation, the linear combination of the inputs is greater than a threshold, still 1, then the output will be a 1. Means I'm going to activate this neuron. That makes sense? So that's what activation means. Activate means my output, I have output, I want to move forward. If the value Z out of the summation is less than that threshold, then the output will be zero. That means I'm not going to send anything out. Okay. So there's no firing, there's no activation of the neuron. So perceptron has this basic structure, basically taking the inputs, weight it, and do two operations. One is summation, the other one is activating. Create an output. Yes. Okay. The cancer cell example, you can wait like 2 minutes. Okay. I'm gonna link that with this. Okay. So that's the perceptron. If you use a diagram, it shows it's pretty much the output. Right? If Z is greater than a T, then you fire it up. Otherwise, you stay at zero. Actually, this page, right? To answer your question, if the activation function is a sigmoid, if the activation function is a sigmoid, then we are pretty much looking at a what? Logistic regression. Right. So 10 minutes ago, I was talking about logistic regression. The first portion of a logistic regression is doing this, taking linear combination of the units. Then if you just use an activation function, which is not a simple threshold logic, replace that with a sigma. As Z is this Z. Then this is equivalent to logistic regression, which will give you binary output, either classified as 0 or 1. Sorry. So that's sigma. So to answer your question, that's your question. That's your output, right? That's your output. Because this is sigma. It will always give you probability. Right? And the input, those input can be your tumor diagnosis output. That become numbers. Or in this case, because cancer cell diagnosis is actually a computer vision problem. So maybe this is replaced by a CNN. But at the end of the day, if you look at this and you realize that logistic regression is just a special case of neural network. Because we are potentially looking at tens of different activation functions. And frankly speaking, we are going to focus on activation function in one of our lectures, because that's the key parameter in any training for neural networks. Okay. Okay, so let me kind of formalize it. What we are looking at is a single layer perceptron. Now we know exactly what happened in this unit. We just combine them together. In the future, you are only going to see a circle, which represents a neuron. But whenever you see a neuron, you know there are two things happening, two operations happening. We're just doing this. Now this is more mathematical, but I will explain that. So first step is doing the calculation of linear combination, right? That's the first part. On the right-hand side, first part of the neuron is to calculate that. Second part is to get an activation function. I use F as an activation function to represent that. You take Z as your input and you activate by applying an F. So what you're getting at the output is an activation output. So those the notations on the right-hand side are mathematical representation, but to represent the functions on the left-hand side. So far, so good? Question? Okay, forward. So this is called a input layer. Input layer. And that's an output layer. But this is just a single neuron, single perceptron. All right. Notation wise, I want you to kind of know the vector notation. This is as much math as you are going to get. Just metrics or vectors. I use vector notation here instead of doing a summation. So the input feature vector X is a column vector. What's the T over there? A small t. Transpose, right, so transpose. So if I transpose a row vector, what does that mean?
A column vector.
It becomes a column vector. So I represent my X as a column vector. Okay. Similarly, I also represent my weight vector as a column vector. So by doing simple algebra, your output Z equal to this linear combination of weights and inputs plus the bias is essentially can be represented by the input vector with the multiplication of the weight vector and the input vector plus a bias. Bias here is actually a scalar. Okay? It's a single number. Okay. We use the term, the notation A to represent the output of the activation. So you see that A equal to Y hat. So you will see sometimes I use A, sometimes I will use Y hat, but recognize that that's the activation output. Okay, so so that's just a notation. Okay, notation. I have a couple of pages to kind of give you a refresher of linear algebra. Not quite sure this is totally necessary, but let me just go through it in a couple of minutes. So we already know what transpose is, right? So this A is a 2x3 matrix. Agree? Why is it 2x3? Excellent. 2 rows and 3 columns, right? So 2x3. A transpose of that will make that 2x2, right? Okay, very good. So this is notation, right? If you transpose a matrix, and essentially the I and J index kind of reverse, right? So your transpose will become a 3x2 matrix. Very good. Okay, so let's kind of explain why we have this notation that X is a row vector, right? And A is a row vector. So if you want to multiply X, which is the input, by weight, in this case, I use A transpose, and this is what we want. This is the single scalar that we want, right? That's no notation of that. I use vector notation throughout this course, so we are not going to go back to this kind of expansion of linear representation. So we'll use vector notation, matrix notation moving forward. Okay. All right. So that's single layer perceptron. Now I want to introduce multi-layer MLP, multi-layers perceptron. By adding an extra layer, which we call hidden layer, for single layer perceptron, you only have input A type output. There's no hidden layer. Multi-layer, you added hidden layer. You can add as many as you want. Multiple hidden layers. Okay. Okay. And we, excuse me. It's called hidden layer for a reason, because when the researchers they develop their model, their algorithms, a lot of times they didn't really show the details. Well, of course, some of the most famous algorithms we know very clearly what's inside each layer. But most of the time, you don't see the hidden layers. So you see a black box. You see the input layer, you see the output layer. You see a black box in between. Of course, that's where the key knowledge is residing, but most of the time you will just see input and output. You will not see what's going on inside the black box or inside the hidden layers. But hidden layers are very important because they actually determine the usefulness and the complexity of your algorithm. Okay. So when we talk about deep learning, what is deep learning? You know, deep learning, what is deep? What is depth?
Training the neural network, like, basically, adjusting the weights of the neural network.
Sure, that's basically what training is for. But when we say deep learning, it means the number of hidden layers. So if you have 30 layers of hidden layers, that means you can go 30 layers deep. A lot of the most sophisticated algorithm has hundreds of layers. So
The problem dictates how many layers are in neural network in terms of like.
sure,
results of the-
it's a very important parameter you can adjust by adding more layers. Sometimes it doesn't work by adding more, but a lot of time there's some sweet spot. Anyway, the key point is deep learning really means how deep is your learning? Really, most of the time means the number of hidden layers that we have in the system. Okay. The other important points for the classical, for the classical neural network is that the output, the input and output are fully connected. Okay. Let me slow it down. It's fully connected. That means all the X1 on the input layer is connected to the next layer, all the neurons in the next layer. There's no missing link. You don't miss anything. Same thing with X2. X2 connected to every neuron in the first hidden layer. Okay. And all the hidden layer neurons also connect to, in this example, very simple, it's just one output layer. So they are all connected to the output layer. So in the most fundamental classical sense, this is all fully connected. Now, of course, there are a lot of training algorithms that can lose some of the connections, make it sparse, but that's another story when we talk about training. So this is called, there's a term for this, called densely, because they are fully connected. Okay, a few things about network capacity, so to speak. So we talk about that. So what is the network width? So that's that. Horizontally from left to right, that's that. vertically from top to bottom, number of neurons per layer. You could have multiple layers. So number of neurons per layer, and you add them up. That's called capacity. But each layer has its own width. You could have 20 in hidden layer number 1. You have 40 in hidden layer number 2. So that's width, number of neurons, vertical in each layer. So that's width. And the total capacity is the total number of neurons in the network. So when you have a very powerful network, it usually means you have a whole bunch of neurons, because neuron means what? Neurons means processing. The more neuron you have, potentially the more processing power you have.
The network capacity also includes the output layer, or just the hidden layer.
Yeah, you can include that. Yeah, because it's also a neuron. Every circle here represents a neuron. Every circle. Right, so this is just a 5-layer neural network. You have 3 hidden layers. There again, which again? What do you mean by again?
So trying to remember that some of the projects were done, and there was a funding thing. It's 1 in 5. We used it like for training the data set that we have. Was that a approach that we? Or is
I'm
it
not exactly sure, but the 3 things that I mentioned are all part of the parameters, right? You can build your models with X amount of layers, hidden layers. You can specify how many neurons that you have for each layer. Okay, those are all parameters you can change. So this is your typical multi-layer neural network, and pay attention that, again, I want to remind you that they are fully connected. Every neuron is fully connected to the next layer, the neurons in the next layer. So this is called fully connected dense layer. Okay. So now we come to the core of this first section. What exactly can a neural network compute? What is it trying to do, right, with all those neurons? But again, come back to this. That's our learning model. Okay. We are dealing with a few different scenarios. We think about different inputs. Okay. So I will give you 3 different cases to explain what neural network can compute. Okay. So we'll look at inputs that are real numbers or Boolean numbers, 0 and 1. Okay. We'll also look at outputs that are either Boolean or real numbers. And so I'll try to at least give you some concept to go home. So those are the 3 things that we'll go through. We'll look at using MLP, which is a multi-layer perceptron. Use that to represent Boolean functions, and not just any Boolean function. Universal. You can use MLP to represent any Boolean function. It's a very important concept. The second one is use MLP to give universal classifier. So that's also very important, because classifier is very important, right? The third one is probably the most important concept, is that you can use MLP to be a universal approximator. So remember, our learning model is to approximate a function using a series of hypotheses to approximate that function that we don't know exactly what it is, that kind of govern the input, the relationship between input and output. So once we go through all those three, I hope you will be able to explain to people, yeah, that's how neural network works. Okay, let's look at the first case. Okay. I'm going to give you a few examples here, okay? Kind of polish up your special memory on visual logic. Okay. So I'm going to assume that the perceptron, the single layer perceptron, because originally Rosenblatt proposed to use perceptron to do Boolean logic. Okay, so this is a very simple, one neuron perceptron. Okay, the number on the arrow is the weight. The input is x and y. They're both Boolean numbers, okay, x and y. And then sorry, too fast. And the number inside the circle, the neuron, is the threshold. Let's go back to the original Rosenblatt model. If it's greater than a threshold, you fire the neuron, you're getting a 1 output. If not, 0. Okay, so it's a simple binary logic problem. Okay. So I want you to look at the first example and tell me that's indeed an AND function. Let's verify that, okay? So what is an AND function? What is an AND? X and Y.
When returns one above or true.
Both has to be
True.
true. So we're good. So we just, I need to kind of refresh your memory. So let's think about X and Y. The X and Y are both 0 and 1 because we're talking about Boolean algebra. Okay. So it's probably easy to see when either one of them is, I mean, only one case that can make this work is when both of them are 1. Right? If X is 1, Y is 1, and X times 1, Y times 1 will be 2. So that's the case that you actually greater or equal to the threshold. Then a 1 will be fired. So the output will be 1. But if either one of them is a 0, or both of them are 0, they are definitely less than 2, right? Makes sense? Because if X is 0, then this path on the in the upper side is 0. So the best you can do is a 1. So it's not going to fire. So all the other three cases, 0, 1, 1, 0, 0, 0, will result in a 0. So that's clearly an AND function. Make sense? Second one, the only thing we change is to change the threshold. And can you imagine this is a OR function? Because the only case that it will not fire a 1 is when both of them are 0. When both of them are 0, your output is 0, so that's the threshold. And all the other three cases will fire the perceptron. So it's AND. Okay. The next one is a NOT function, inverse. Look with me here. So if you have a 0 here, 0 times -1 is 0. It will fire, right? Of -1, a 0 becomes a 1. But if you have a 1, this will be -1, which is less than the threshold. So it becomes 0. So by setting up the threshold properly, this simple single layer perceptron can do those three basic AND, OR, and NOT gates. All right. So that's what made the whole AI research very exciting in the late 50s is that, oh shoot, yeah, okay. If we can prove that well, this perceptron can implement all kinds of Boolean array, Boolean algebra, then we probably have something special. Because if you think about it, in nowadays, all our computers are built based on binary logic. Binary logic, arithmetics, calculations, everything can be represented by binary gates. That's how we build the chips, right? How we build computers, especially on the chip level. It's all gates. You boil it down to it's all gates. But unfortunately, that's not the case. They run into a problem. They cannot represent exclusive OR. You can't make this simple as a simple perceptron implement exclusive OR. Okay. So because that's what exclusive OR is, but you just can't find the right the right combination of weights and threshold. Okay. But that's not the end of the day. Because that's like multiple layers of perceptron. We can make it work. Let's stop right here. But let's go through this. Why two-layer perceptron actually implement something a little bit more sophisticated, such as this exclusive OR. I already kind of give you the answer, but let's walk through this. Okay. Let's focus on the upper branch, the first neuron in the first this hidden layer, right? This is a hidden layer. Yeah, the first hidden layer. The upper neuron has the threshold of 1, and the weights going into this neuron are both 1. Okay. So based on what we just learned in the previous page, this is an OR, right? It's an OR function. And the one in the lower branch, the lower neuron, is actually quite the opposite of the end function we looked at earlier, because everything is inverted from the previous x and y function. So let me skip the detail. What you will end up with is actually an x bar, which is inverse of x, and inverse 1. So what essentially out of the first hidden layer are two functions. One is x or y. The other one is x bar or y. Okay. Then you can just build your own truth table. Use this output layer. You convince yourself the output is actually exclusive. You do this as an exercise. But things get better because now we started to use multiple layer perceptron. And just by simply add one more layer, we solve exclusive OR, which is a big deal. And we all know exclusive OR is very important. You can probably think about how to do NOR. NOR is pretty important too. Okay. On NAND. The chip is built on NOR gate and NAND gates. Okay. But anyway, that's another story. But here's where we start the excitement. Okay. That we can actually give me 3 more minutes. I think I want to finish this universal Boolean function. So I want to kind of extend that example into a statement that if I give you a Boolean function, it can be arbitrary, you can represent it using multiple layer of perceptron. Absolutely. This one is not that hard to understand. This will result to that. This one will eventually result to that logic function. So my statement here is that MLPs can compute any Boolean functions because the basic idea is they can emulate individual gates. What are the most fundamental gates? And or not exclusive or. Pretty much it. If you can emulate all those gates, then a combination of them can be used to assimilate, to implement all the other universal Boolean functions. So that's very important. Okay, that's very, very important. Let's do one exercise. One exercise. I'll let you go. Typical truth table. I'll give you all once, so you know how to build this truth table. Can you write down the truth function for this? What is y? When y equal to 1, that means you can just take a look at each combination and figure out what make that one possible. Right? So if you look at the first row, what would make that one possible?
X3 and X3 and X4.
X3 and X4. But if you want to also include X1 and X2, what would that be? And X5?
Not a bar.
Not, right? Not a bar. Same thing. If there is a 1, there's no bar. If there's a 0, there's a bar. And at the end, what do you do with those 5 different scenarios, 6 different scenarios? You order them together, right? Because either one of them is a 1. Output is a 1. Make sense? Okay. So there you go. Well, I'll try to simplify. Okay, I just derive the most fundamental logic function based on the truth table. So that's what it is, right? When there's a 0, you have a bar. There's a 1, there's no bar. You order them together. So that's your first order of that's exactly the output of the Boolean function. Now the question is, hey, how do you actually compute this using MLP? You have 6 neurons in the hidden layer. And you have the output layer at the top. Now, of course, you have to figure out the weights and the threshold. You know it's gonna work. So conceptually, to implement an arbitrary Boolean function like that, you just basically, for each of the neuron in the hidden layer, you have fully connected layer, the hidden. Right? And each one of them is n. X1, X2, X3, X5, 2, X5, they are all n together, either by a bar or no bar. Yeah, n together. Even though we didn't put an n in between, but it's an n function, right? That's an explicit OR function. So in the hidden layer, you AND all those inputs together. And on the output layer, you use a generalized OR function. You OR them together. So that's how you actually can create this Boolean function, this logic function using the neural network. Okay. I think that's probably it for this section. Yes, indeed it is. Does that make sense to you? Okay. So that's case number 1. We'll pick it up next Wednesday.
Sorry.
Wednesdays.
Okay. All right.
Keep your email when we're doing.
There's Labor Day on Monday, so there's no class. But you will have your first quiz this weekend. The way it works is it will be available on Friday. You have 3 days to work on it. You probably will have 10 minutes to work on the quiz. You have 2 chances, so don't worry. You're miserable in the first try. I always want you to have multiple tries to get the best answer. And you will also have your first homework. will not be due until a week after the delivery. Okay? Oh, yeah.
So what's the quiz cover?
All the way to today.
Oh.
Yeah, the first 2 weeks.